So multiples are quite common phenomenon in seismic data. Can you hear me from the back? Okay, thanks. So in many cases, those multiples are regarded as noise, and people are working very hard and try to remove those multiples. But we cannot deny the fact that those multiples also contain a wealth of information. So if we can use those multiples, we can use them to improve the resolution of our reservoir imaging. What I am interested in is the water layer multiples at the receiver side. Those multiples are primary waves, and it goes up and hit the ocean surface, and then they get reflected. Those multiples can be recorded by OBS, short for ocean bottom seismometers. So for this, conventionally, we have both source and the receivers near the ocean surface. I will use a red dot to represent source and blue triangles to represent receivers. And in the following slides, I will follow the convention to use OS to represent ocean surface and OB to represent ocean bottom. So this is a typical rate path of acoustic wave field. So in this case, we can only see P waves. Now, if we think about elastic wave field, although in the water layer, we'll still only have P waves. But once the P wave hits the ocean bottom, it will transmit into both P and S waves. I will use the red line to represent S wave and the blue line to represent P waves. And then both the P and the S waves will hit the reflector and get reflected into P and S waves. This makes the wave field much more complicated than the acoustic case. And then when they travel back into the water layer, all of them will convert into P waves. So although the data we get from at the receivers are only pure P waves, some of them are converted from S waves and at the ocean bottom. So in some cases, people are using ocean bottom seismometers. Instead of replacing the receivers on the ocean surface, they place the receivers on the ocean bottom. The ocean bottom seismometer contains a hydrophone and geophone. A hydrophone will record the pressure of the wave field, and the geophone records 3 components of the particle velocity. So one thing we cannot ignore in the OBS data is the water layer multiples are quite strong. If we leave those multiples in our OBS data and do migration, those multiples will cross-correlate with some other wave modes, and we will get artifacts in our final imaging. So in many cases, people try to remove the multiples. But what I'm interested in is I want to use the multiples to do imaging. This idea has been performed under acoustic case. Today, I will generalize the idea of using those multiples to do elastic imaging. The simplest way to approach to realize the elastic imaging using multiples is to use the mirror imaging. I mirror the receivers over the ocean surface to the dashed line locations and do the back propagation from the mirror the receiver locations. The only thing we should remember is because the multiples are reflected from the free surface, which is the ocean surface. So if we want to inject them back from the mirror the receiver locations, we have to change the sign of the data. So now our first question is, how can we get multiples and the primaries separately from the OBS data? From this cartoon, we can see for the primary waves, actually, when they hit the ocean bottom, they are outgoing waves. And the multiple waves, they are downgoing waves. So this gives us a criteria to separate the OBS data into outgoing and downgoing waves. But a thing about the downgoing waves is it also contains other waves. For example, it has higher order multiples that bounce between ocean bottom and ocean surface more than once. But they are weaker than the first order multiples, so we ignore them here. Those are the equations we use for up and down separation. U represents the outgoing waves and D represents the downgoing waves. The P is the pressure which is recorded by the hydrophone, and the VZ is a vertical velocity, vertical component of the particle velocity, which is recorded by the geophone. If the ocean bottom is not horizontal, what we should do is we should rotate the particle velocity such that the vertical component corresponds to the normal of the ocean bottom. Here, the alpha is a scaling factor. There are a lot of research about how to choose the alpha wisely and to make the separation more completely. But this topic is a little bit more involved than I have time for now. Now our next step, after getting the up, down, and upgoing waves and downgoing waves, and in which we regard them as primary waves and multiples, and we will proceed our elastic reverse migration. Our next step is to do receiver side and source side wave field reconstruction. To demonstrate those procedures, I will use a very simple model. This model contains one horizontal reflector at 1.2 kilometers, which is shown with the yellow dots. And the ocean bottom is shown with the magenta line. And I have my source on the ocean bottom at 2.5, and ocean surface at 2.5. Sorry. And now I'm showing a series of snapshots of the wave field. This is the source side wave field. When the wave is propagating through the ocean bottom, it would transmit into P and S waves. And when they both hit the reflector, which are shown with the indicates in the yellow dots, both of them will reflect into P and S waves, which makes the wave field much more complicated than the acoustic case. So before applying imaging condition, what I do is I would decompose the wave field into P and S modes. If the medium we are using is isotropic, we can simply apply the Helmholtz decomposition, which is shown here now. And P is a P wave, and S is a S wave vector. And if it is a 2E case, the S vector only has one non-zero component. So let's go back to our wave field. After applying Helmholtz decomposition, we get the P mode and the S mode. Notice that there is no P waves in the water layer. After getting the P and S modes in the wave field, both in the source side and the receiver side, now we can apply the elastic imaging condition. I will still follow the imaging condition proposed by Yan and Sava in 2007, that they combine the different wave modes in the source and receiver side wave field. I and J can represent P or S. That means if we have I and J both P, that means we combine the P mode in both source side and the receiver side, and we get a PP image. Now let's go back to our cartoon I showed earlier. So this is the source side wave field, and this is the ideal receiver side wave field. The reason we call it ideal receiver side wave field is because although as some of the P waves are recorded by the receivers are converted from S waves, and some of the P waves are just transmitted from P waves. When they inject back into our model, all of those P waves will convert into P and S wave modes. So those waves that we don't want, I'm showing here using the dashed line, we call them fake wave modes. those fake wave modes will cross-correlate with the short-side wave field, and then we'll get artifacts. I will talk about how we deal with those artifacts later, but firstly, let's take a look at those images we get first. So this is our model, because we assume that we know where the ocean bottom is. So if we have any artifacts in the water layer, we can just mute them because we know there will be no reflectors in the water layer. And in the following, I will just show the image in the white box. Now, the top of the model becomes the ocean bottom. We combine the P wave modes in both the source side and the receiver side and get the PP image. In the PP image, we have both the true events at 2.5 kilometers and artifacts below the true events. In a similar way, we get a PS image and the SP image. In those images, what we should have noticed is at normal incident angle, there's no energy. And from the left side to the right side of the source, the true event has a polarity change. And this is the SS image. In the SS image, the artifacts is even more stronger than the true event. So this requires us have to find a way to remove those artifacts before stacking those images over shots. So let's go back to the PP image. We still have one thing about the artifacts is, as most of the artifacts, they are spatially inconsistent from shot to shot. That means if we remove the shots horizontally, the artifacts will not stay in the same location. But for the true events, they will stay still at the same location, like vertically. So this gives an idea. If we have many shots on the ocean bottom, we can subtract. We'll get many images. We get one image for one shot. So we subtract the image at the same point, let's say 2.5 kilometers, and combine all the traces at 2.5 kilometers to get a common image together. We call CIG. And this is our PPCIG. I use a red circle to show the true events. That is what we want to keep, because they are horizontal. That means they don't change their locations with we move our shot. And on the other hand, we want to remove those events with move out. We applied one filter in the radon domain. So firstly, we do the radon transform to transform this image to radon domain, and now the horizontal axis becomes slope. So what we want to keep are the events at around slope 0. So by applying a very simple mask, we only keep the events at slope 0, and the other events with large slope now are muted. Then we convert it back into our original domain, and in this domain you can see most of the artifacts has been removed, and the true reflector now is preserved. I will show our result with the model. I built this model based on Marmosi, and I add a water layer above the model. Both the P velocity and S velocity model I'm using are smoothed, and I keep the sparse contrast in the density model. I have 288 shots along evenly distributed on the ocean surface. And in a similar way, I will apply the filter before stacking those images overshot. So I got the CIG at 1.5 kilometers. And this is a PPCIG. You can see we have those true events which are horizontal, and we have some events that artifacts they have moved out. And also we have some low frequency events. Some of them are from the diving waves. After applying the filter, we only keep the events with the events that are horizontal. Similarly, we do the same filter to PSCIG and SPCIG. And those two CIGs, we can see that at normal incidence, there's no energy still. And from the left side to the right side of the image, there still have a polarity change. But in this image at 1.5 kilometers, we can see the left side of the image is much more stronger than the right side. But this is not always true for all the CIGs, so we cannot stack them over shots directly. This is the SS image. At normal incident angle, there is still no energy, but from the left side to the right side, there is no polarity change, so we can still stack those SS images overshot after applying the filter. So this is our image using the multiples, only the multiples. For comparison, I also do the PP imaging using the primary waves. You can see in the deep part, it's almost of the same. But for the shallow part, the PP image using the primaries are a little bit stronger than the multiples. This is because now for the primaries, we're placing the receivers very close to the ocean bottom, so they can collect more reflections from the shallower part interfaces, which have a large, very huge slope. This is the SS image using multiples, and this is the image using primary waves. SS images always have a smaller angle illumination compared to PP image. This is because in the same layer, the S wave is always traveling in a smaller velocity than the P waves. So to summarize my talk today, firstly, we are interested in imaging to do elastic imaging using the OBS multiples. The part I'm especially interested is we are using the surface-related multiples. That is, we're using the first-order water layer multiples at the receiver side. This will provide us more information about the subsurface. And because we are using elastic forward modeling code for both source side and receiver side wave field construction, and we still keep the interface of the ocean bottom in every model, so we'll get the wave mode conversion at ocean bottom. This conversion will give us P and S modes. In this way, we can get P, S, SP, and SS and PP images at the same time. But in our image, we have many artifacts because of the fake wave modes. So we're trying to use filter to remove those artifacts before stack all those images overshot. And during our work, there are many interesting topics that we want to do in the future. The firstly is, as now we are still using the synthetic model, we generate the primary waves and the multiples separately. But if we have to deal with the OBS real data, we have to implement the up and down separations to separate the upgoing and downgoing waves from the OBS data. This will be a very interesting research topic. And next, for the real acquisition geometry, the OBS are sparsely distributed on the ocean bottom because of their high cost. In the future, we will try to to modify our acquisition geometry to get close to the real acquisition. And because our basic purpose of using multiples is we try to use multiples to improve our resolution about the reservoir imaging. So we will try to combine the primary waves and the multiple waves imaging together to get a better image. And then, as I just in my examples, I just show you the PP image and SS image because I can't get the PS and SP images to stack them over shots because of the polarity change exists. So it's interesting if we can get more options to choose a new elastic imaging condition.
Sorry.
If we can get another kind of imaging condition, we can compute impedance instead of reflectivity. In that way, we might get rid of the polarity change in our imaging. So we can also get the PS and SP image. We're looking forward to those future work. And at this point, I look forward to your feedback and any questions you might have. Thank you.